Hi, year 11. We're going to look at polynomials as our next lesson. Okay, so what is a polynomial? A polynomial is a smooth and continuous function. This means there are no jumps or gaps between them. So here are all examples of polynomials. Here's a linear polynomial. Here's a cubic polynomial. And this has got 1, 2, 4. Would be a quartic polynomial. You can see they're all smooth, no gaps, no jumps. Now, what about algebraically? Well, a polynomial is a function that can be written as a sum where the powers are positive integers or 0 and the coefficients are constants. Now, when we say constants, that means the coefficients, such as the -5 there, it can be any real number. It could be a decimal, okay? It could be a fraction. So I could, for example, write p of x equals 0.1 x to the 7 minus 2/3 x plus square root of 6. So any real number for the coefficients, but the powers have to be positive integers or 0, okay? Now have a look at the next one. You can see here I don't have a positive integer for the power. So this particular function is not a polynomial. All right, and over here, have a look. You can see that the power is -2. It's not a positive integer, so that's not a polynomial either. Okay, but the first one is. Right, so that brings us to a definition that we can write for a polynomial in general. So a polynomial is a function that can be written as a sum. Okay, it can be written as a sum, but the powers are positive, integers are 0, and the coefficients are constants. Now, when we're talking about the coefficients, we're talking about the term in front of the pronumeral term. So Pn is a coefficient, and this one here, Pn minus 1 is a coefficient. Here, P3 is a coefficient, and P2 is a coefficient, P1, and lastly P0. And just be aware when we write the P, we don't go P2, okay? What we do is we write it as a subscript, P2. Usually it's a lowercase, okay, because we reserve the uppercase for the polynomial itself. Okay, so I've circled all the coefficients. Now the leading term. Now for the leading term is, it's this one, it's Pn x to the n. It's a term with the highest power, okay, the highest power. So that's important. So up here, the leading term is actually this whole thing here, Pn x to the n. The leading coefficient, or the leading coefficient is what I've circled here, which is Pn. It's the coefficient next to the pronumeral with the highest power. P0 is called the constant term because it remains constant. Okay, so P0 is the term which has no pronumeral next to it. See, it's just all by itself, so it'll be like a number. So if we went back up here, the P0 term would be the 6. That's the P0 term. Okay, so it's the term without the pronumeral. The degree of the polynomial is the index of the leading term. So it's the index or power. So that means we're talking about the power of the leading term. Okay, so if you come back up here to the first polynomial we looked at, you can see the leading term has a highest power of 7. So we say the degree of that polynomial is 7. So the degree refers to the highest power of the polynomial. Now, lastly, just a bit of terminology here. What is a monic polynomial? Okay, so monic just means that you've got a leading coefficient of 1. So for example, if I wrote down y is equal to x cubed minus 7x squared. That is a polynomial. But notice that the leading coefficient here is 1. So that's what we call a monic polynomial. All right, first example for you to look at. All right, so I want you to fill in these blanks here. So let's have a look. Leading term is the term with the highest power, 2x to the 7. Constant term is the term without the pronumeral, that's 6. Leading coefficient is 2. The degree of this polynomial is 7. Okay, let's look at another one. And here we go. Now what's the degree? We've got to find the term with the highest power. This is the term with the highest power. So you can see the highest power is 3, the degree is 3. The leading coefficient is the term next to the pronumeral which has the highest power, so it's -4. The leading term is minus 4x cubed. And the constant term in this case is the term without the pronumeral, which is 11. Okay, it's pretty straightforward. Now let's have a look at polynomial equations. All right, so P of x is P of x equals 0 is called a polynomial equation of degree n, where P of x is your polynomial, whatever it may be. Okay, so in this case, the general polynomial has got a leading term of P n x to the n, so the degree of that polynomial is n. So have a look at this one. Here's a polynomial equation. Right, you can see here's my leading term, right? The degree is 3, isn't it? So the highest power. So this is a polynomial equation of degree 3. Now, some more terminology. The values of x that satisfy this equation are called the roots or solutions. So the x values, which will give me 0, are called the roots or solutions of the equation. They're also called the zeros of the polynomial. They mean the same thing. It's called the zeros of the polynomial because the x values which I put in to get 0 makes the polynomial equal to 0. So that's why they're called the zeros. Now, let's have a look at this. For P of x equals 3, x minus 2x minus 5x plus 1, the zeros are x equals 2, x equals 5, x equals minus 1, because they're the values that I put into the polynomial to get 0. Okay, if I put 2 into this polynomial, I'll get 2 minus 2 is 0, and 0 times all the other brackets will be 0. Okay, now what about the next example? For the polynomial equation, 3x minus 2, x minus 5x plus 1, the roots are x equals 2, x equals 5, x equals minus 1. Right? The roots are also referred to as the solutions of the equation. So really the same sort of thing. Zeros, roots, solutions, they mean the same thing, which is basically the x values which you sub into the polynomial to get 0. Okay, so let's have a look at this one. First example, find the zeros. Okay, that means solve the equation. Okay, so what we're going to do first is write down, we've got to put this equation equal to 0 first to find the zeros, and then factorize. Okay, so it's going to give you x equals 0 and x equals 5. All right, now, what about the next one? To show that this has got no zeros. Well, this is a quadratic, isn't it? So let's first of all write down the equation we've got to solve. So we've got to put that equal to 0. Now, the zeros are the x-intercepts, aren't they? So if this, and this is a concave up parabola. So if we're going to show that it's got no zeros or no x-intercepts, it's got to be above the x-axis. And you know, for a quadratic, that means delta must be negative. So all I've got to do here is find out what delta is for this quadratic. So delta is equal to minus b, so that's minus -1. Sorry, that's not right, is it? Getting carried away there. Delta is equal to b squared minus 4ac. So that's going to be minus 1 squared minus 4 outside of 1 outside of c gives you 1 minus 16, which equals negative 15. Right? So therefore no solution. Therefore no real roots. Okay, so no real zeros. All right, next question. Graphing polynomials. Okay, so let's have a look. Here's our general polynomial. P of x, okay, equals Pn x to the n all the way down to P0. Now let's see if we can see some patterns. We're going to look at some even degree polynomials, okay? So here's an even degree polynomial. How do I know? Here's the equation. If you look at the leading term, what would the leading term be? What do you think the leading term would be? This one. Leading term, well, you can have 0.1 there, certainly. If you multiply the x terms out, you're going to get x to the 4. Okay, so this is a polynomial of even degree, isn't it? Degree 4, in fact. Now, have a look where the ends of the function begin and end. So here's one end, here's another end. Now, it ends in the first quadrant. It begins in the second quadrant. And the other thing to notice about this particular polynomial is the leading coefficient is positive. Okay, so what I would say is that the leading coefficient Pn is greater than 0. All right, now let's have a look at this one over here. The second one you can see here, we've got beginning and ending. Now, where does it begin and end? Begins in the third quadrant. And it ends in the fourth quadrant. Oops. Okay, now what about the leading term? What's the leading term going to be? Well, you can see it's negative 0.1. If you multiply those x terms out, the highest x term will be x to the 4, won't it? Think about it, you've got x times x times x times x, x to the 4. Okay, now notice the leading term here is negative. Okay, so P n less than 0. All right, so what's our conclusion then? Well, if you've got even degree, and the leading coefficient is positive, so even degree and positive, then it begins, it's going to be in the first and the second quadrant. In fact, it begins in the second, and finishes in the first. Now, the other case to consider is if you've got a negative leading coefficient and the degree is even, then you're like beginning in the third quadrant and finishing in the fourth quadrant. So that applies to that one, and that applies to that one. Okay, let's have a look at an odd degree. So here we go. Here's two odd degree polynomials. And notice where they begin and end. Okay, so if we're looking at, let's change colors here. So it begins in the third quadrant. And it ends in the first quadrant. Okay, now what about the leading term? See if you can pick what the leading term will be. Well, if you look at the equation, you're going to have 0.1 0.01. And if you multiply those x terms out, you're going to get x to the 5. So the leading term is x to the 5. So it's got odd degree, doesn't it? Okay, so if you take to get the leading term, you just take the x terms there and multiply them. Okay. All right, and what else do you notice about the leading coefficient? The leading coefficient there is positive. So what we're going to then say is that if you've got an odd degree and the leading coefficient is positive, you begin in the third quadrant and finish in the first. And let's look over here. Now we're beginning in the second and finishing in the fourth, aren't we? Okay, so there's the second quadrant. Here's the fourth quadrant. So we're beginning in the second and finishing in the fourth. Now what about the leading term? The leading term, what's that equal to? We've got minus 0.01. Now if you multiply all the x's out, 1, 2, 3, 4, 5, you're going to have x to the 5 again. Okay, notice that the leading coefficient is negative, right? P and less than 0. So our conclusion will be, if you've got a odd degree polynomial, okay, and we can tell it's odd degree because you've got degree 5 for the leading term, then you've got a negative leading coefficient, then you begin in the second quadrant and finish in the fourth. And over here, if you've got an odd degree, and you've got a positive leading coefficient, positive there, and you're going to be starting in the third quadrant and finishing in the first quadrant. Okay, so so we put that down as a summary down here. All right, so you've got positive leading coefficient, odd degree, then you're in the first and third quadrant. So you begin in the third and finish in the first. If you've got a negative leading coefficient and odd degree, then you start in the second and finish in the fourth. Okay, so starting in the second, finishing in the fourth. All right. Now, how do you remember all that sort of stuff? This is how I remember it. I just think of the most simple even degree polynomial I can think of, which is y equals x squared. And I think about this, that's got a positive leading coefficient of 1. So clearly it starts in the second and finishes in the first. And for a negative quadratic or negative parabola through the origin, this is the most simple one I can think of. You know how to draw those automatically. That begins in the third, finishes in the fourth. Okay, so that's how I remember the even degree cases. For the odd degree, I think of what's the simplest odd degree polynomial with a positive leading coefficient. It's this one, y equals x cubed. It's got a leading coefficient of 1. Okay, so leading coefficient of 1 there. And well, I know how to draw those, and it begins there and finishes there. So it begins in the third, finishes in the first. And I think of the most simple cubic with a negative leading coefficient, and that's y equals minus x cubed, and I know how to draw that. So that begins in the second and finishes in the fourth. So if you remember these basic graphs, then you're fine to remember everything about the odd and even degrees up here. Okay, so just think that the odd and even degrees can be simplified down to just a y equals x squared and y equals x cubed case. All right. Now comes for the action part. You're going to now sketch these polynomials. So first things first. Well, let's have a look at what the leading term looks like. Okay, so leading term. Okay, leading term. Well, for the leading term, what have we got? We've got, if I take the x terms, x times x times x times x, that's just going to be x to the 4. Okay, so it's even degree, and the coefficient is 1 there. So I've got a positive leading coefficient and it's even degree. So think back to the most simple even degree polynomial you can think of. That's like y equals x squared. Okay, so straight away you know that we're going to start here and finish there. Okay, next let's think of what we can do to find the x-intercepts. Well, to find the x-intercepts, I've got to solve x plus 1, x minus 2, x plus 3, x minus 4 equal to 0. And just from inspection, we can see that x will be -1, it'll be 2, it'll be -3, and 4. Okay, so straight away over here, I can put some numbers on here. 1, 2, 3, 4, -1, -2, -3, -4. Okay, and let's put where the numbers are. So we're going to have -1. There's 1, 2, -3, and 4. Okay, so those are the 4 places that will cross the x-axis. Now, what about the y-intercept? To get the y-intercept, just sub in x equals 0, and that's going to give you y equals, okay, so you're going to have 1, and then -2, and then 3, and then -4. So just be aware you can replace p of x there with y, okay, just to make it the labelling easier. So 1 times -2 times 3, -6, it's going to be 24. So now we're ready to sketch. Okay, so I know where I'm starting, I know where I'm finishing. So let's have a look. So coming down here, and I'm going to have to turn back after that, turning back, and then crossing, going through 2, and turning back, and finishing in that quadrant there. Okay, so just from that bit out there. All right, so that's the function. Now, you might be saying, well, what about the y-intercept? Well, I've only got one number I have to show, so I don't need a proper scale here. I can just say, well, that is 24, just like that. All right, so make sure you put arrows on either end, and there's your polynomial of even degree with positive coefficient, the positive leading coefficient. Okay, try the next one. So let's start off by saying, what's the leading term? Okay. Leading term. Okay, well, we can have a -2 there, obviously. And x times x times x is x cubed. So the leading term is -2x cubed. Now, this is, think of the most simple cubic that you can think of with a negative coefficient, and it's this one. Oops. Okay, so that means I'm starting here and finishing here. Good. Now, what about finding the zeros? So you're just going to put the equation equal to 0. And just from inspection, you can see that x equals 1, 3, and -4. So straight away over here, we can put some numbers: 1, 2, 3, 4, -1, -2, -3, -4. And let's put the intercepts there. So we've got 1 at 1 there, we'll put a little dot, then at 3, and then at -4. And what about the y-intercept? Y-intercept, well, you put x equals 0. So you're going to get y equals -2, brackets, -1 times -3 times 4. So it gives you -2 times -1 is 2, times -3 is -6, and times 4 is -24. Okay, so I know where I'm starting, I know where I'm finishing. So let's go. So going through there, a bit wobbly. Now I'm going to have to turn back. And then I'm going to have to turn back and come through there. And then I finish there. Okay, good. Okay, so I finished in the second. So I started in the second and finished in the fourth. And just drop out these bits that are unnecessary. Okay, now, just last of all, you have to put your y-intercept on there. There's only one number you have to show, so no need for a proper scale. And negative 24 just there. That'll do. All right. Now, let's have a look at something called double and triple roots. What is a double root? Well, here's a double root. A double root is when you've got a repeated factor in your polynomial. Okay, so if I was to write this out in a different way, I could write this as x minus 3, and x plus 2. Okay, so you can see here I've got a repeated factor of x minus 3. All right, and therefore we say it's got a double root. Now what's so special about a double root? Well, here the double root is at x equals 3. Okay, double root, in this case, double root at x equals 3. And if you're wondering why we call it a double root, well, if I was to write out the roots, right, what would I have? X equals 3, 3, and negative 2. So you do have a double root there, right? Double root. Now, what's special about this graphically is that at the double root, you have a turning point right on the x-axis. It touches the x-axis. It doesn't cross it, it just touches it. We actually say the x-axis is a tangent to the polynomial at that point. So for a double root, you've got your turning point right there at x equals 3, because the double root is at x equals 3, and that's exactly where the turning point occurs. Okay, so let's have a look at triple roots. Triple roots. Okay, what's special about triple roots? Well, where's the triple root on this one? Well, I can see I've actually got a double and a triple, don't I? I've got a double root at x equals 3, and I've got a triple root at x equals negative 2. And what's special about this is that at the triple root, we have a horizontal inflection on the x-axis. What does that mean? It just means that the polynomial is perfectly horizontal just at x equals negative 2 in this case. So there's my inflection point right there. Okay, so at that exact point, the curve is perfectly horizontal. So when you're sketching that, you've got to show the curve to be horizontal. Okay, so triple root, just there at x equals negative 2, right? So let's write that down. Triple root at x equals negative 2, right? Now, to have a play with that, actually before we have a play with that, do you notice where the double root is? The double root is x equals 3, and that's why you've got a turning point, right? Turning point here. And if you were going to sketch this just from the equation, you could look at the leading term. What's the leading term? Leading term is negative 0.02. Now, the first bracket gives me x squared as the highest degree, and the second bracket is x cubed. So combine those together, you've got x to the 5. So that's the leading term. It's odd degree, and it's negative leading coefficient. So you begin in the second quadrant, finish in the fourth. Okay, and just to have a muck around with this so you can see what happens, I will click on Desmos. And I'll be typing in y equals, let's put a a double root at x equals 1. So I put x minus 1, then I would go Alt 2, no, that doesn't work, Shift 6 and then 2 gives me the power, and then let's put a triple root at x equals negative 4. That means we're going to have x plus 4 as a factor. Shift 6 to get the power, and then I'll put a triple root there. So you can see I've got the turning point at x equals 1, and I've got the horizontal part of the polynomial at x equals negative 4. Now if I wanted to squash that down a bit, I could put a really small constant at the front. There we go. That'll do. So that compresses the polynomial. So you can see here I've got a horizontal inflection there and a turning point at x equals 1. So go to that site, Desmos, it's on your notes, and just practice putting in different double roots and triple roots to make sure you understand the concept. Okay, so now we've got the idea, we can do some sketching. Okay, so here we've got a double root. Yep, and let's also start just by beginning in the same way. Leading term. Well, there's x, and the leading term in the second bracket will be x squared, and then you've got the x there. Combine those together, you're going to have x to the 4, right? And think of this as 1x to the 4. And the simplest even degree polynomial with a positive coefficient I can think of as y equals x squared. That means I'm going to be beginning here, finishing there. Next, I'll be looking at finding the zeros. X plus 2, x minus 1 squared, x plus 1 equals 0. So you can see here that the zeros will be x equals negative 2, x equals 1, x equals negative 1. Now the other thing to note is that there is a double root at x equals 1, right? Here. That's your double root there. Okay, x equals 1. All right, now what about the y-intercept? We need to know that. So sub in x equals 0. You will get y equals 2 brackets minus 1 squared and then 1. Now that will simplify to 2, won't it? Right, so let's put some numbers on our number plane. Okay, minus 1, minus 2, minus 3, minus 4. Okay, and let's put our intercepts in. Let's just go back to full screen mode. Okay. And all right, so what do we got? We've got negative 2. We have 1. And we have negative 1. Okay, now don't forget though that at x equals 1 here, right, you have your double root. So maybe put a little arrow there just to remind yourself. All right, so I'm going to come, starting from here, right, I'm starting in this quadrant here. Now, starting this quadrant, I'm going to come down, then I'm going to come up, then I've got to come down, and don't forget I've got a turning point just here, right, because it's a double root. Close enough. There we go. All right, so I almost got the turning point perfectly at x equals 1, but it's close enough. You can see there that that's what it looks like. Now your y-intercept is at 2, so you should just put a 2 there on the y-axis. Okay, let's have a look at the next one, triple root. So straight away though, I'm just going to look at the leading term. Leading term. So you've got x there, you've got x cubed there because of that 3, and then you've got minus x here. So you multiply those together, you're going to get x to minus x to the 5. All right, so odd degree, negative leading coefficient. So again, I just go back to my simple odd degree with negative leading coefficient, and it's this one, y equals negative x cubed, so it goes like that. So I know that I'm going to start here and finish here. All right, that's the leading term. Now what about the next bit? We can find the zeros. Okay, so I'm going to solve x. In other words, I'm just finding the x-intercepts here. Okay, so you can see that x equals 3, negative 1, and 2. All right. Now, what about the y-intercept? Put in x equals 0. You're going to get y equals negative 3 outside of 1 cubed outside of 2. And that's going to give you negative 6. All right. And the other thing you could say is that there is a triple root at x equals negative 1. All right, so let's put some numbers on the number plane. Let's have a look. Okay, so 1 here, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. Okay, and let's also put our intercepts on there. So 3, negative 1, and 2. So negative 1 there, 2 there, and 3 here. Now, where is the double root? It's at x equals negative 1, isn't it? So here's my double root. So I might just put a little arrow here to remind myself to do double root. Now remember with a double root, not double root, triple root. Triple root, you need to have the curve needs to be horizontal. Here it is, horizontal. Okay, so I'm actually going to start here, and I've got to come in, I've got to flatten out. So I've got to flatten out just there. Didn't do such a good job there, so maybe I'll come in a little bit wider. Okay, so difficult with this digital pen. So yeah, I'm coming in. Oops. Try again. Okay, so I'm coming in. I've got to be perfectly horizontal there, and then I've got to come down, and then up, and then down through the other intercept, and finish there. Okay. Now the horizontal part of my function there is a bit exaggerated. It's easy to do with a normal pen. In fact, you can see here, this is where the horizontal part should be, right at x equals negative 1. I've done it a little bit too long, but it's only a sketch. All right, now the only thing I haven't put in yet is my y-intercept. So that is at negative 6. So I'm just going to say here, it's pretty hard to write there. Let's put a little arrow there. That should be negative. Actually, I'll get rid of that. Hang on. And I'll put, okay, negative 6 just there. Okay, there we go. All right, next one. Last one, actually. Last one. Now, first of all, leading term's easy here, isn't it? It's already there for us. Leading term is 1x to the 4. Okay, so the simplest even degree with positive leading coefficient is your basic parabola. Bit of a poor sketch there, but there it is. So that means I'm going to start there, finish there. All right, now, a couple of things we could do here. We have to put this in factored form, don't we? So I'm going to, now to solve the equation equal to 0, will give me the x-intercept. So notice that x squared is actually a common factor here. So I've got to factorize. Plus 2 minus 3 equals 0. Then I still have to factor it further, don't I? I can factor that's a quadratic. Now, x and x, 3 and 1. I need a positive 2, so I'm going to have a positive 3 and minus 1. So straight away from that equation, I can see x equals 0, x equals 1, x equals negative 3. And I've actually got a double root here, don't I? Okay, because of that squared term. So I could say that I've got a double root at x equals 0. Okay, and what about the y-intercept? Y-intercept, we'll sub in x equals 0, and you'll get y equals, well, 0, won't you? So let's put some numbers here. 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. And let's put the intercept. So we've got 0 there. Then we've got 1. And then we've got negative 3 over here. Okay, now don't forget, at this point here, you're going to have a double root. So let's draw it. I know where I'm starting. Here we go. So starting in this quadrant, and then turning point, because it's a double root. Then back up through here, and there we go. That's what it looks like. Okay, so there's your model function. Okay, so you can now do the set questions, exercise 3.13 from your textbook. Right, so it's